Howdy and welcome to my channel. On this video I'd like to cover the Mastech MS5308, which is an auto-ranging LCR meter. And prices I kind of checked today during this filming kind of were around $200 to about $350 depending on where you buy them. I think I paid around $200 off of eBay maybe 6 months ago, free shipping from China. I checked on the Mastech, at least one of their sites, and couldn't really find this model listed. So kind of take a look at the case. Case is really nice. I really like it. Zippers are good. Everything's done well. Has little pockets up here, extra ones, divider. So all pretty nice. And we'll take I'll move it off to the side and then just take the items out of the case, kind of show them to you. The items in the case, you get some software for data logging and the drivers, and talk more about this a little bit later. You get the LCR meter, which we'll talk about more shortly. You get a manual that's pretty poor, and I would recommend probably downloading other company manuals that use the same chipset, which would have a lot more useful information in them. You get a blade connection to some clips that plug into it. You get an optical connection to USB for connecting to your computer. You get a power supply unit so that you can plug it into AC. And I think this has some major problems. We'll take a look at it in more detail. I had some bad luck with it, along with the AC cord that comes with it. And you also get another tweezer set to the blade, which I don't have. I took it apart, and I'll explain that in a couple minutes. But this is the tweezers that it comes with, and I basically wanted this blade connection, so I unsoldered it. It was really easy, a couple of screws and just unsolder it. Made it simple. Taking a little bit closer look, this is the blade right here. It's a 5-wire system. You have a 4-wire Kelvin connections to these clips right here. You also have a ground guard shield that goes through there. You can unscrew this. It's really easy to just take it apart. That's what I did to the one that came with the tweezers, and I replaced it with a sort of a test jig. So I'll move this out of the way. And so here's the actual piece that I took off of the clips. And then I used a metal enclosure and then mounted B and C connectors to it. And you can't really probably see it, but I've labeled them so I know which are which. And then you can use like the 4 B and C, and you can get the same kind of clips. As you can look, they look pretty much identical off of eBay, for example, at a very reasonable price. And you can also have B and C to additional tweezers and buy a lot of additional extra connections. My plan is to take this off and put a PC board on here through the B and Cs, so I can have just 2 little plates there I can tap components to real quickly. And again, tried to watch the shielding, put some rubber feet on it, made a metal enclosure. And I found out that using the calibration system on the meter, I was able to get rid of most of the parasitic problems and everything, and really going directly into the meter or through all of this wiring harness and everything, it was about a 2% error down at the 10 picofarad range. So I felt reasonably comfortable. Again, I'm really a hobbyist, and this is just pretty much for fun. Okay, taking a little bit closer look at the LCR meter. On the back of it, it's got a huge bail that opens up for support. And as you can see, the overall unit is reasonably large, and therefore maybe not completely portable. It does have a little strap on here that's, so you can get your hand in there and grip it. It's hard plastic, and a negative of that is also there's no rubber feet or anything on the bails. This is an anti-static mat, so it sits real nice and doesn't move around at all. But on slippier surfaces, or smoother surfaces, it tends to slide around. It would have been nice if they added some little rubberized feet to the bail and to the bottom of this. And apparently this particular case is used also in other different systems and test equipment. It's powered by 8 AA batteries. They're on the back here. And couple of screws lift it out, and it actually comes out very nicely. And we'll open it up and take it apart and show you the internals and everything. And I'll zoom in a little bit closer. I also believe, I haven't done it, but when we take it apart, I think these are sewn on straps right here, but I think you can actually remove them once the two pieces break apart. So if you wanted to take this off, you could. Okay, here's the front of the unit. We have our power button over here. We have our Kelvin 4-wire system, and again with a grounded shielding. They also say do not apply voltages greater than 30 volts to input terminals and discharge capacitors before testing. Here I've connected up a garden variety capacitor, but I did take it over to a lab, and they had some very high-end LCR testers, and they measured it, and so they came out with a value that we can sort of compare with this one. So even though it's not a precision capacitor, when you turn the unit on, it displays everything for about 2 seconds. It goes into its auto LCR mode by default, which means it does identification of the component. It also chooses the series parallel. Here we're doing a capacitance series, it found, and the default test frequency is 1 kilohertz. And according to the lab, this should be a 345.4 nanofarad capacitor, and we're reading 345.7. Again, it may toggle around the least significant digit. And their dissipation factor was 0.004, so we're reading the same dissipation factor. Again, I did 4 or 5 different capacitors and coils, and I've kind of checked it out, and everything does seem to be in spec, seems to be a pretty good reading. Even though I have a capacitor hooked up, just like to go through some of the function keys and show you how it works. Again, here is your main function key that is in auto mode, so it's auto-detected LCR. You can override that and push it and cycle through the ones that you'd like to do. So when you click this, you notice the LCR disappeared off of there. It's still in auto mode because it's auto ranging, so sort of a semi-automatic mode. And notice it's wanting to measure series inductance. If you press it again, you get series capacitance right here. And of course, that's the value that we just had on there. In this mode, you can change the different frequencies by pressing the frequency button. So we're at 1 kilohertz. If we press it again, there's 10 kilohertz. And it updates the value, and the values might shift slightly. And same with the dissipation factors. Because Q and dissipation factor are frequency dependent. Press at 100 kilohertz, and you can just sort of cycle around through each one of these. 100 hertz, 120 hertz, and back to the 1 kilohertz. So the frequency button then will cycle through those. Best selection a lot of times is if you have data sheets or something, try to choose a frequency that's either the frequency they tested at or close to that. Again, there are component analyzers that do much better and can do it at maybe the operating frequency. So this only has a small selection. It does give a little bit of help, especially for power supplies, things like that, which we'll take a look at. Across here you have the RS-232 button. When you push this, it simply turns the RS-232 on, and this basically button is used to stop and start your data acquisition system when you have it connected up through an I/O port at the top to your computer. More about that, we'll show that a little bit later. The hold button is pretty primitive. When you press the hold button, you get a hold indicator, and effectively if you then remove the component, you can see that nothing changes on the display. So basically just freezes the display. Backlight, we press this button right here. You won't see too much of a difference. It's really a nice backlight. It illuminates the entire display and makes everything crisp, and we can turn the lights out and take a closer look at it, but it's very good. This one is your secondary parameters possibly. Here's where you have the dissipation factor, the Q, the ESR, equivalent series resistance. It doesn't show it, but there's actually a theta, which is the phase angle, and it is on there and you cycle through it. So typically capacitors, you do dissipation factor. Inductors, you would do the Q. They are reciprocal properties. ESR can be very helpful. Measures its effective or equivalent series resistance, 2.38 ohms up here. And then it does, even though it doesn't show it on the button, it does have theta, which is the phase angle. And so a purely resistive circuit would have a 0-degree phase angle, for example, between the current and the voltage. A capacitor would have a minus 90-degree phase angle if it was pure capacitance. And a pure inductor would have a plus 90-degree phase angle, indicating whether you're leading or lagging your voltages and currents. This one, since it's almost 90 degrees, it's telling you it is pretty much capacitance for the dominant characteristic of the component. but we saw there's a little bit of series resistance. Interesting thing about the three passive components is that they're really not ideal. So a resistor, for example, can have the characteristics of the other two, same with a capacitor or inductor. A good example is if you have a wire wound resistor that has resistance of the wire. You then have the wire coiled around, which makes an inductor, and if the coils are insulated, which they should be, from each other, you have distributed capacitance. So all of a sudden you have a model, for example, a resistor really having characteristics of capacitance and inductance. And the same thing with the other two components. So you might do a first approximation model, second, third. It really depends on your application. The next button is setup, which is used with the sorting function, and we'll show that in just a little bit. This is your series parallel selection, whether you want a series or parallel model and test the component. I'll talk a little bit about that in a few minutes. We have a sorting button so that you can set up for a certain percentage and to do a pass-fail of the component. You have a rail button where you can have a reference component and then compare all the others to that. A range on this is plus or minus 99%. Again, we've already done the frequency. And in some of the setups, you have an enter key for your selection. Also, for the keys have arrows so that you can increase and decrease and move left or right to make different numerical changes under the sorting setup modes. Okay, I've already calibrated this unit to this particular fixture. You can have different fixtures, for example, and then you should then calibrate them. As I indicated before, some units have a button on the front panel that you press for calibration. This one actually has a little recessed hole in the top right here, and when I got it, it's all scratched up, so they must have been doing a lot of calibration. I found that if you use a 3mm by 12mm machine screw, it actually fits in the hole up there without bouncing around much. So you can just drop it right in there, and then you have a little place where you can press it. Again, normally I would set it up on the particular jig, and I'm not going to be doing calibrations every minute. So if we kind of back out to here where you can see also the clip leads, what you do is you basically disconnect, you set up the jig you want. And this whole process is to get rid of the parasitics and stray capacitance, inductance, resistances. So you're sort of calibrating the meter to the test leads and fixtures. So what you do is you press this to enter that mode, and you'll get an open indicator, and open means have the test leads open so they're not connected together. And then you press it a second time and it'll do a 30-second countdown as it does its calibration. So I'm just going to press this again. You can see we have the 30 right up there, and it's counting down. Again, I'll edit this out so you're not seeing the whole thing. So here we're approaching the 0. And we get a pass, which means it's done the calibration for the leads being open. The next operation is you want to short the leads together. And you press the button again, and it'll go into short mode. And it's the same process. Press the button again. It'll do a 30-second countdown as it's doing its calibration and everything. It also has a little cal indicator up here while it's doing that process. And we're down to the 2 seconds, and we get a pass, and now the system's calibrated. Press it one more time, takes it out of calibration, and you're now back into normal mode of operation. And again, if you changed your leads or the fixture, you would then want to calibrate to that. And I had no problems with this meter calibrating to my little test jig. And again, you'd want the extra additional leads also connected. So you want to have all the connections in there while you're doing the calibration. This is a little shielded coil with ferrite tuning, and in the laboratory LCR meter I set it to 160 microhenries. So we were on auto LCR detect, so see if it can figure out that this is a coil. So we're going to connect it up. Oops. And it comes up with 160.4 with a Q of 0.344. And again, now that Q is a function of frequency, and so we're at 1 kilohertz. Real danger with this, when you're thinking about Qs, you want to maybe check the data sheets and find out what frequency it was measured at, if your unit can do that. But a lot of times if you're designing like an RF circuit, and you do this measurement, you have this Q of 0.3, or maybe you have a Q of 20 or something like that. But then you are measuring it at 1,000 cycles and you put it into a 170 megahertz circuit, all of a sudden the Q might be 2. And you're wondering what happened. It went from 20 down to 2. So Q does change the function of frequency. Normally increases with frequency up to a certain point and starts falling off. So just important to always remember that, the limitations of your instrument. Okay, one nice thing on the LCR meter is you can use it to measure ohmic values, resistances. This one is a little 10 watt 0.1 ohm 1% resistor, so I can connect this up. Make sure my hands aren't touching anything, although it's really low value. And you can see we're reading a series resistance of 0.1 ohms. And the phase angle is 0.0 degrees, which is trying to indicate that it's very, very resistive, at least at the 1 kilohertz test frequency. Here's an electrolytic capacitor. Stamped out value is 390 microfarads, 63 working volts. And it's supposed to be a low ESR capacitor. So again, it has a polarity since it's electrolytic, so I'll put the minus to the negative side and connect up the positive. And it identifies it as about 372 microfarads. Again, it was printed at 390, but it's not that high a precision. However, if you check its data sheet, it was measured because it might be used in a full wave power supply, which would have a ripple frequency of 120 hertz for North America, 60 cycle line frequency, or 100 hertz for other countries in the world that would be running on 50 cycles. And so let's actually go and adjust that. So I'm going to cycle through and go to 120 hertz and reread it. And you notice that we actually went up quite a bit there. We went to 386.2. Again, it's stamped at 390. So as I keep saying, important if you can, if you know what the test frequencies are, what they measured at, it would be good to try to do the same thing when you're measuring them with this meter. Let's take a look at the sorting function. Here I have a bunch of 6.8 nanofarad capacitors, and of course I'll just do a couple to show the operation of sorting. Okay, here I've connected up a capacitor of the 6.8 nanofarad. You can see this one's reading 6.6 at a frequency of 120 hertz. And so what I'm going to do is go into the sorting mode. To do that, you can't be in the auto mode. So I'm going to take it out of auto and then cycle down through until I get my capacitor. And again, this is a small value capacitor. I'm going to use the series capacitive model right there. Then I'm going to push the sorting button. And you can see it passed mainly because it actually just took the value that I had there, and it says it's within 1%. You can choose the value that you're going to do. So if we press setup, we can go through here and we can choose the range by using these two arrow keys. So if you notice we're at 6.6, and you see each time I press it, it moves back and forth across there. So I'm going to just leave it where it is, press the enter key, I'm okay with that, and then now it allows us to change it. Since this is supposed to be a 6.8, I will just use the down arrow keys to take the least significant digit, take it down to 0, then move over one, and I want to take this one up to 0.8, and then press my enter key. And now this is my new value. It's asking us what tolerance, and you can cycle through the different tolerances. We have 1% there, 2%, 5%, 10%, 20%, minus 20 plus 80%, which sounds strange, but that's for electrolytics and filter capacitors. And then we can go down to 1/4%, 0.5%, so quite a few choices, 1%. I'm going to go ahead and set it up for 10%. So there's my 10%, press enter, and we're ready. And what it's doing is it's now comparing it to the marked value, and it's just giving us a pass, fail, go, no go situation. And the secondary display is telling you the actual value of the component. So I could take this one out and hook up another one to it. And again, notice this one's higher, but it's still within its 10%, so it indicates that it's a pass. If you like to actually know percentage differences from a reference component, you'd use the rel command. So to get into that one, to leave the sorting button, you simply just repress it again and it takes it out of sorting mode. And now we're back into normal measurements. Okay, to use the rel mode, you just take a capacitor that you'd like to be the standard. Here I've got a capacitor. You simply clip it in like you're doing a normal measurement. Once that's selected, just press the rel key. You'll get a rel, and then you'll get a percent difference from that value that you selected. So if I take that capacitor off and put in another capacitor, you can see that the value from the reference one that I just had in there, it's a 6% higher. And you can just go through and then cycle through and you're getting percentages. And again, this will do plus or minus 99%. In this section of the video, I'm just checking the excitation signal coming from the tester. I have a 10 megohm oscilloscope probe with a shunting capacitance somewhere between 15 and 20 picofarads. The unit is actually reading the parallel capacitance at 18.9 picofarads. We're on a 1 kilohertz signal, and we can now see it's definitely a sine wave. It's centered around ground. It's about 1.8 volts peak to peak, and the frequency, I'm not sure you can read this, but it is at 1 kilohertz. And we could cycle through the different frequencies. We'll go ahead and just put it right on the CP, and we have 1K, and here's 10K, and the unit's reading 10K, and the peak-to-peak signal is about the same. 1.86 volts peak to peak. Again, we don't have a component in here other than the actual component is the test leads, oscilloscope probe. And press it again, 100 kilohertz. And we are getting 100 kilohertz, and it's dropped down a little bit to about 1.5, 1.6 volts peak to peak. Again, with just the scope probe, the other two frequencies, 100 hertz and 120, was also about 1.86 volts peak to peak, and the frequencies were pretty good. Here, though, I've put the capacitor back in just to show that there is an impedance to that capacitor, and obviously as frequency goes up, capacitive reactance goes down, and you have more of a loading effect. Some meters have a level output control, or even a constant AGC system, to try to maintain at a particular value that they want. This unit doesn't do that. So if you notice when we're at the 120 hertz, I'm still reading about the 1.86 volts. But as I go up into frequency, the capacitive reactance goes down, and of course it loads the test signal. And we can see it's not dropped too much. It's down to 1.82, was 1.86 before. Go to 10 kilohertz, and here you can see a really noticeable drop. We're down to 1.22 volts peak to peak, and of course at the 100K will be the smallest signal out, and it looks almost like a noise. So increase the sensitivity a little bit. A little bit of trouble triggering on there. We could bandwidth limit it. And shown here, what I've just done is simply a bandwidth limiter, turn the bandwidth limiter on, so we're not running at the full 100 megahertz, much reduced. And we can see the peak to peak, we're getting down to about 130 millivolts of excitation signal. We can also check if we're trying to measure a DC, even though there's a capacitor, just as a quick example, we can go to DC, and again, it takes a long time for it to set up. And we can see it's putting out a DC value, and it's 500 millivolts per centimeter, and it's indicating that it's approximately 775 millivolts RMS since it's a DC. So a little bit less than 1 volt on this particular unit. Another simple check, and just kind of a handy thing to do with a LCR meter, is we have some coaxial cable here. This is RG58AU. It's made by Consolidated. I looked it up on the internet, and notice that the far end here is not connected to anything, so it's basically just two pieces of metal separated by a dielectric. You have a capacitor. And according to the data sheet, it's supposed to be 29.5 picofarads per foot. So this is a little bit crude. What I've just done is taken a dual banana to BNC, put it on there, And I'm just going to, hopefully these will hold on. I'm just going to kind of grab them on. And then I'm going to go ahead and fix capacitance. And we come up with 776.5 picofarads. This is supposed to be a 25-foot cable. If we divide this value by 29.5 picofarads, it comes out a little over 26 feet. So it's kind of a handy little trick sometimes if you have a spool of coaxial cable or some type of cabling that has high capacitance, and maybe it's a 300-foot spool and you don't know how much you have left on it, you can make a measurement. That's provided that the output, at the other end of the cable is open. If it's shorted, you might be able to measure the resistance, which is kind of tough, or you can measure the inductance. So open, generally you measure the capacitive characteristic. Shorted, you generally can measure the inductance to determine it. Use a little 5.5 timer and a good oscilloscope, and you can make a little time domain reflectometer. And the nice thing is, again, if you had this and it was in the wall and it was 150 feet long, you could then figure out if it had an open, you could determine it's approximately 25 feet. Maybe that would help you locate it in the conduit or something. So kind of handy little tricks to use with this. Okay, in this shot, I'm going to go ahead and take the unit apart. I actually did take it apart earlier to remove the strap, and it was really simple to do. And there's not a lot in here because it's a couple of chips, two big LSI chips that do pretty much everything. So if you lift the bail right here, there's two screws that you would undo. And this will give you access to the battery compartment. And it has some 3 fingers up on this side of it, so you kind of lift it up this way and then pull it out. And one nice thing is these screws do go into metal inserts on these. The others are self-tapping screws. And there are some screws underneath the battery, so you have to pop the batteries out. So I'm going to go ahead and stop it just to undo the screws for us. Okay, I've removed the screws. There were 2 here, 2 again up at the top, and 2 in the battery compartment. And then you might have to use a plastic tool or something to kind of pry it open a little bit. It is, 2 wires do connect to it, so when you lift it up, there is a connection right here that you can unplug it and then set that aside. There's nothing back here, no shielding or anything like that. Okay, using the bail to kind of hold it up in this particular position. As you see, it's mainly 2 chips here from Cyrus Tech that set up the whole unit. I'll zoom in close on each one of them. But basically, this one would be the analog input unit along with some resistive switching for ranges. Has a crystal. There's another crystal up here, and then this one is sort of a multi-mode unit that does also all the computations for dissipation factor, Q, phase angle. It also interfaces with the keys on the front panel, and it helps for driving the LCD display. Up here at the top is your power input for when you want to plug it into AC, your calibration reset, and your optical output. And again, I'll zoom in on all these. And here's our buzzer over on this side. Not too much on here. The quality of the board and everything looks nice. The soldering that was placing the surface mount components on here also looks good. This over here is the power on-off switch. So again, I'll move into this section first, followed by this section, and then take a quick look at this section up here. So here's a close-up view of the first chip, which is the front end basically, and it's an ES51920S right here. It looks like it says 24 on there. I'm assuming that might be a 24 megahertz crystal. It's got some capacitors and a lot of the capacitor components here sprinkled around. And here's the second circuit right up at this point. It's the ES519190. And there are a couple little calibration pots on the board. You can see one up here. And then there's pretty much a kludge. Here's your ground coming in off for your external power. And they just tack soldered it to one of the resistors on their R16. So that doesn't look too nice. Looks like over here where they had 12 volt ground, they had probably a plug and a header there. So that, normally these 2 wires would have plugged into this. And I don't know what happened there. Maybe it was a Friday or something. And then this is a shot of the top of the unit. And if I kind of hold my hand tilted up, you can see that it's the IR transmitter. There's only one IR transmitter and the other one's missing, so it's unidirectional. So when you're doing data logging, everything, it's just going one way. Again, there's a monstrous cal button here, and then this is the input for the external DC. The unit they give you is rated at 12 volts, 1 amp, pretty healthy. Okay, and then I'll just kind of hold it and just tilt it up a little bit, give a quick scan again of the board just so you can kind of see it. Okay, taking a look just to see what the current draw on this is. They are 8 AA batteries that were in the back, and they're in series, so it's a total of 12 volts. And so I've set the power supply at 12 volts over here, and I've connected it up, and then I'll just kind of hold one of the leads to it and turn it on. So we'll put it in here, make a connection. And you can see it's around 14 milliamps, and I have flipped through a bunch of the different modes, and it seems to be about 14 milliamps all the time. Obviously, I didn't check the backlight, which would be drawing more. And here I'm just repeating it again. I just try to put a capacitor on there, see if it makes any difference. And you can see it's actually changed a little bit. There's 14.5 again. I've tried a couple different capacitors and inductor. It seems to all be about the same. A brief comment, as I indicated before, there is a bar graph down here. It has a 0 to 100%, and wasn't really too sure, at least in the manual I didn't see any comments about what it's used for, its purpose. And basically this does have ranges by a factor of 2. It's like 200 ohms to 2,000 ohms and so on and so forth. If you notice, if we assume this is a 2,000 ohm scale, and I've put a 1K resistor in here, notice it's at 50%. And then if I start incrementing, just adding more resistances to this thing, you can see that we're just getting higher and higher percentages on the scale. And then when it finally goes to the next scale, notice we just went over to the 2,000, now we're going 2,000 to 20,000. It drops back down and gives you that percentage. So I guess it gives you kind of a relative idea of what percentage of the scale you're using on that particular range. Personally, I don't really see any need for it. I don't think I'm going to have a need for it anyway. As I mentioned earlier, it says do not apply a voltage greater than 30 volts to the input terminals. And actually, I'd be a little scared to apply any voltage to it. I do have another LCR meter that allows you to apply a DC bias. You connect it up to the back and you can go up to certain values. And that can really be handy by putting certain components maybe under their operating voltages possibly. Also Vericap diodes, that'd be really handy and it works really well. And a lot of coils, might be specified out for particular current flow through them. And again, this is pretty light duty, and I would use the other meter for those applications. So whether or not you can inject a DC voltage along in here to do a bias, you might be able to. I sure would not want to try that. This next area actually may be a defect in my unit, so maybe this isn't universal. For people that have them, maybe they can make a comment in the notes below. But if you can see, I have this is again not a high accuracy resistor on the switch box, but I have about a 20K resistor in there, 19.72K, and we're running on batteries. They do give you a supplied switching power supply. As you can see right here, we have 12 volts at 1 amp and 110 volts at 240. And if I plug that in to the unit, you can see it's absolutely terrible. It's coming up at 29.85 K ohms. So huge percent error, maybe what, 30% or so error. Now we could also try it to go on to the DC. I'll stop the video just because it takes that 10 seconds to change. And here I've hooked it up for the DC test signal. So we're measuring the DC resistance. And again, if I plug it in, it's 19.84 K, which is about what the other one was, so that would be okay. But then when I go AC, external power, we have about 25K, not as bad as the 30K, but still not acceptable. So again, I don't know if mine's defective or I did check the non-loaded output of the switching power supply. It looked pretty good. It had a little high frequency noise on it, but didn't think it was too bad. And what I am going to do is want to connect it and test it with a load, so it's something more I have to pursue, maybe the the power supply is not good, or I can try injecting in another power supply to see if that solves the problem. But at least right now with the materials I'm given, it doesn't really work. Okay, I'd like to try this one more time, this little test. Here though I have a capacitor instead of the resistor connected up. Notice it shows the APO that we're running off the batteries and has automatic power off. I'm going to go ahead and plug this in. We can see it's 151 nanofarads approximately. Plug it in, the APO goes off. And notice it doesn't change much at all. So the problem with this seems to be on the resistor modes of operation. Here's a quick look at the data logging software. I've turned my aperture on my camera down a bit just so that the screen shows up better, CRT, so it's a little bit dark. But at least you can see that it's online. There's a place over here that indicates that it's online, and I'm on COM port 4, and I am connected. And you can see across here we've got the value and the phase angle, so it's echoing what's on this particular screen. Okay, here I've just zoomed in so you can take a little bit closer look. Again, like I said, just repeating, COM port 4, we're connected, we're online. There's our data list, and here's our graphing. I did capture a couple just for this, so I can reset that and clear out the min-max of it. You can set the Y right here through several choices, or you can increase or decrease them with these buttons. You can also bring up a separate window with this kind of zoomed in on this particular display right here. So I'll go ahead and just capture something. If I press the reset button that's on the tester, it will start going through and give us a capture of some values. I'll go ahead and just press it again to stop it. And here you see we have our value and the dissipation factor to test frequency 1K. Here's the particular values. You can print them, or you can save them to an Excel spreadsheet. And again, as I indicated, you can zoom in on this, so you can click this and you can see we're changing the vertical ranges on there. You can also float over it and it gives you those values of those test points right there that it's captured it at. If I want to port it off to a spreadsheet, you just click it like this, do test 2, save, and then I can bring up, going off here, bring up my Excel or my spreadsheet. This one's Open Office. And you can see we can open it up. So we go there, open, select test 2, click open. It's asking you how you want it for delimited. It is comma delimited, okay. And there you can see we have our values. So you get the mode that it's in, the sample value that it took, the magnitude of the component, its units, and a timestamp. And then of course if you had a whole bunch of these that are changing or you're doing different sampling, you can do graphing, whatever else obviously you want once you're in this domain. One last quick one again, I can just click on this. These buttons move you back and forth if you have more pages on this. And this brings up, if you see a zoomed in window, and again it gives you the values as you go across. Reasonably simple, I mean it does operate, but not too feature rich. It also indicates I think it can only handle 50,000 samples. Again, you can turn the APO off when you're running that mode so it doesn't shut down on you. Okay, so what do I think of the unit? The Mastech MS5308 LCR tester. You get a lot of accessories, has a nice case, large display with good backlight, easy to read, AC and DC operation, and reasonably accurate measurements, and you get quite a few choices there with dissipation, Q, ESR, and others. Well, probably on the negative side, a very poor manual, but you can usually find another company's manual online with no problem. And a Cal button on the front panel might be a nice touch. You do only get basic data logging, no DC bias or excitation level controls, amplitude level controls. For my unit may only be my problem. I have a DC resistor problem when I'm on external power supply. But overall, thumbs up, and especially considering the price.